So we've got this 6-step process. Every question will go through this. Step 2 here goes back to Chelsea's question, decide on a significance level. In reality, that will always be given to you in the question that you are doing. Okay, and this will become clearer as we go through an example. And we're going to start off by doing example 1. So example 1 says, it's known that students joining year 7 have weights that are normally distributed with a mean of 70 and a standard deviation of 7.5. This is where you think, well, how is it known? And it's known because the great God of statistics has told the person who set the question. In real life, it wouldn't be known. But you just got to accept for now that the great God of statistics has just told you that, and just get on with the question. A random sample of 90 students from the latest intake has a mean of 71.6 kilograms. Here's the question. Is there evidence at the 5% significance level that the mean weight of the new intake basically has changed, has deviated from the normal pattern of 70? So you've got a sample, it's more than 70. So does that mean that actually they're not normal 77.5 squared? Or could they just be that and you just pick some of the heavier people in your sample? That's what we're trying to work out. Okay? So, I'm going to take the question off the board, but you've got it in front of you. And what we'll go through now is how we would answer that question. So, what was step 1? What was step 1? Can somebody just tell me?
Decide the alternative of the null.
Yeah, decide the alternative of the null hypothesis. Okay, so we always start our question off with a null hypothesis. The null hypothesis, remember, is no one's guilty, nothing's actually changed, nothing bad going on. So a null hypothesis will be that the mean weight of the new intake is still 70 kilograms. Nothing has actually changed. So you'd write it down as a sentence in an A-level question, and then you'd write it down in notation. Well, the mean weight is mu, so we are saying that mu equals 70 kilograms. This year group are not guilty of being fat. Okay, that's a null hypothesis. So the alternative hypothesis, well, looking back at the question, it said, is there significant evidence that the mean weight is more than 70? So there's your alternative hypothesis. The mean weight of the new intake is more than 70 kilograms. That's our sentence. And if we put that in notation, it's mu is greater than 70 kilograms. Sometimes this will be a greater than, sometimes it'll be a less than, sometimes it'll just be a not equal to. Just, is it different in any way whatsoever?
Do you have to mention the 5%?
We will do in a minute. That's in step 2 that will come in. So we're still at step 1 at the moment. But this one here, we always need to make one other observation here. We're only interested in a one sort of deviation. The question only said, is it more than 70? Not is it different from 70? And because it's an inequality sign here, greater than, this is what we call a one-tailed test. A one-tailed test. And it's called that because if I sketch a normal distribution curve, under our null hypothesis, it was that mu was 70. We are just interested in, has mu shifted over here? Is it greater than? That's a one-tail test. If it said, is it just no longer 70, they may be interested in here or here. That would be called a two-tail test. So we've got a one-tail test. So if you want to make a note somewhere that if you use that sign or that sign in your alternative hypothesis, it's called a one-tail test. Or if you used a not equal to sign in your hypothesis, then that will be called a two-tail test. Well, that is step 1 dealt with. Step 1 was define the null and alternative hypothesis. We've done it in words and we've done it in symbols. So step 2 was decide on a significance level. Well, the decision's been taken for you. Step 2, we were told that we are to use 5% significance level. And that will always be given to you in the question. Step 3, calculate the critical value and critical region. This is what we haven't really talked about yet. And I think for step 3, which is what we're doing here, this is step 3, that was step 2, a sketch is often very helpful. So, if we do a sketch, the null hypothesis says mu equals 70. We are interested in a one-tailed test at 5%. So, put somewhere on here, do some shading in. That shading in is supposed to represent 5% of your area. We mentioned a critical value. Our critical value is going to be a weight called C, where 5% of the weight exceeds C. If this really is distributed, this curve here, if this really is distributed, normal, 70, 7.5 squared, because that's what it says in the null hypothesis. So we start off believing that to be true. So that is believed to start with. That is believed, and that's from the null hypothesis, H0. So what we're going to do in a minute, we're going to work out this critical value C, and if the mean of our sample is in this shaded area here, if a mean of our sample is greater than C, then we are going to conclude they are actually heavier as a year group than averaging 70. Because the chance of our sample just getting those people being that is 5% or less, and we're declaring that's so unlikely that actually the whole year group is actually heavier. If our sample mean is less than that C value, then we're going to conclude no, they're not heavier. Our sample, has not concluded that they are heavier. We could have just got that by chance. So this C here is going to be our critical value, and we are going to use our test statistic. And the only test statistic we have is the mean of the weights, W. Now we know that the weights are distributed normally 77.5 squared. So what do we know about the distribution of W bar, the mean of those weights?
70 times 90.
Sorry?
70 times 90.
We're not adding them up, so it's not going to be that. Central limit theorem here, this is the sample mean. Yeah, you're going the right way there, Billy, yeah. Remember, this will be mu sigma squared over n. This is where the central limit theorem is coming in. It's the distribution of the sample means. So our W bar is going to be distributed mu, which is 70, sigma squared, which is 7.5 squared, divided by n, how many people were in our sample, and that was 90. So that is the distribution of W bar. And that value over there, if you want to work that out, is 0.625. And what we're going to do now is we're going to find this value of C. We're going to find this critical value C. Sorry? This is... Well, no, not at the moment. We're still in step 3. We're still in step 3 at the moment. We calculate the critical value in the critical region. So we're going to find this critical value C. We always do less than probabilities. So the probability that the weight is less than C, according to our diagram up here, is what? If 5% is on the right, what's to the left of it? 95%, yeah. Okay? So that's where that line there comes from. So turning that into phi notation, it's C minus the mean over the standard deviation that we are dealing with here. We are going to put that equal to our 0.95. So I'm going to have 5 of. Our critical value we don't know. Our mean for W bar is 70. Our sigma squared over n is 0.625, and that needs to be square rooted down there. And I get that 0.95. Is everybody happy what I've done there so far? So we're going back to normal distribution probabilities and phi's. So that 70 is that mu, that sigma squared over n is here, and I'm square rooting it. Now if I want to find out the c, what's my next step? Yeah, I need to anti-phi. I need to anti-phi both sides, which means on the left I just get rid of the phi symbol, and on the right I anti-phi 0.95. If you anti-phi 0.95, what do you get? 1.645 is correct. Remember, when you're anti-phiing, these values like 0.95 and common ones at the bottom of the tables, you can use this bit here. You don't have to look in the middle. And you will memorise soon that one there and that one there, because we use them an awful lot. This 0.95 one here is used for one tail tests at 5%. This one here is used for two tail tests at 5%. You'll be using these values an awful lot. You will remember them soon. So that's where that's coming from. So yeah, that one there is 1.645. So you now rearrange that equation to find out what C is. So can you just get your calculators out, rearrange that to find out what C is, our critical value? 71.3, did you say?
77.
I've got 71.3 here. Okay. 71.3 should be what we've got. So I'm just going to sketch again that diagram we had earlier. We had mu was 70. We've now worked out 71.3 is where 5% of our probability lies. Okay, and down here we're looking at W bar, the sample means. And we are going to, now in step 3 it said calculate the critical value. Well, the critical value is 71.3. The critical region is the region to the right of that. So our critical region is W bar being greater than 71.3. That's step 3 done. Step 4 is calculate the test statistic. Well, the test statistic was given to us in the question. It said the sample had a mean of 71.6. So if I just move that up there. Moving on to step 4, our test statistic is our sample mean, and we were told that in the question that W bar, the mean of the sample weights, was 71.6 kilograms, which is about here somewhere. It's in the critical region. So because this was in the critical region, we can move on to step 5, which is deciding the outcome of the test. What did we say earlier? What did I say earlier? If the sample comes in the critical region, what do we conclude? It's not H0. If it's over here, it's such an extreme value that we're saying they're guilty of being fat. Okay? So we could say as our test statistic.
Just number 5.
Yeah, okay. As our test statistic is in the critical region, that means it's unlikely that it could have occurred by chance.
Can you push up?
Yeah, it's unlikely it could have occurred by chance. I just got to stop the video there because I realise I've run out of time for this clip, and I'll continue another one.